Yesterday we learned that in gases the molecules are not at rest. The molecules are continuously moving, right? So we are going to continue with that idea. We'll build up on it. We'll understand what is pressure, right? Understand what is pressure and why pressure is exerted by a gas on the walls. We'll also learn what is temperature. Okay. So in this chapter, we're going to explore the two very important quantities that are useful for studying gaseous systems, that is pressure and temperature. Okay. So hopefully you do remember that animation that I did show you yesterday, where molecules are just going around here and there, right? Okay. Understanding that animation and being able to imagine that one is the key, really. Okay. If you will be able to remember what was shown, then you're going to find this chapter quite a bit easier. Okay. So in this lecture, we are going to cover what is pressure. See, first of all, I'm going to explain why does a gas exert pressure on the wall. Okay, why should there even be something like pressure? Well, think of this. Suppose there is a container in which gas is filled. Let's say this container. And suppose we will talk about the right wall. Okay, excuse the horrible drawing here. Okay, but I'm sure you can imagine that if you think that these gas molecules are moving occasionally, while they are moving randomly, they will definitely collide with the wall. You understand what I'm saying? The gas molecules will definitely collide with a wall, right? Okay, and once again, just to remind you that the collisions are going to be perfectly elastic collisions, right? Don't forget, the collisions are perfectly elastic collisions, because if it's inelastic, then energy will be lost and gradually all the molecules will slow down, and then all the molecules won't be moving at all, which is not true, right? If that was the case, what we observe around us, the dust particles floating here and there, uh, such other light fluffy objects floating here and there, we won't see that. Okay, so we know it's perfectly elastic collision even with the wall, right? Even with the wall. So now that is what allows us to derive or understand why pressure would be there. This is when a molecule, okay, let's just say that this is this is a wall, right? And a molecule comes in, let's say at some angle, and hits here, and then bounces off, right? Hopefully you remember that this is what elastic collision looks like, right? So if the collision is elastic, this angle and this angle are going to be same, right? If the collision is elastic, then both these angles are going to be same. Also, we can consider the wall to be immovable. And we can consider the wall to be immovable or rigid, and that is a reasonable assumption. Okay, right? So it's that when the molecule with a very little mass m strikes it, the wall is not going anywhere, right? The wall will just remain stationary, right? So what this means is, because if this is an elastic collision, then you're going to notice that the speed with which this was coming in here, right? The speed with which this was coming in, it will go back with the same speed. Only then it's going to be a perfectly elastic collision, right? So I can say that for a single, for a single collision, for a single collision, if mass is m and speed is supposed to be I, okay, then the change in momentum, collision change is velocity. I agree, but not the speed. Remember, perfectly elastic collision and one thing is not moving. So kinetic energy should remain same before and after. Initial kinetic energy half mvi squared. Final kinetic energy will also be half mvi squared. So velocity will change. That's right, but the speed will not change if this wall is immovable, right? So ultimately, what we are having is as follows. If you just take the x component, right, of this particle's momentum, so Ex before collision, right, is going to be mvi cos theta. I'm sure everyone gets that. Which we can also write as mvx. Is it clear what I've written here? Okay. Now after collision, when this molecule is going in this direction, you see the momentum after collision that I am writing in green, right, will in x component it has reversed, because before collision it was moving towards the right hand side, okay, but after collision it's now moving towards the left hand side. So that's why this will become minus mvi cos theta or minus mvx. So effectively happened what has effectively happened is that the direction has reversed, okay, as far as x component of momentum is concerned. Is it okay? Because now it's going in the left direction, right side positive, then left side has to be negative. Okay, so this is what we are seeing. So now if I want to find out what's the change in momentum, see one more thing. Let's have a look at y components also. Let's have a look at y components of momentum. You're going to find that there is no change in it. Okay, I'm just writing it now. Just give me 1 second. If you're going to look at the y component, there is no change. Let's see why I am saying that. So y component of momentum. So first of all, py. Okay, it's going to be. Look at this arrow. Initially, before collision, this is going towards the right side and bottom. Do you agree that py is going to be minus mvi sine theta? Yes or no? Negative because it's going down. Okay, towards negative y-axis. Now after collision, you have a look at this one going there. So once again, py, this is before and after. After collision, once again py is minus mvi sine theta. Remember, it is still going down. Third quadrant. X component negative, y component also negative. So both are negative in the third quadrant where this one goes. Right? So you see there is no change. Before and after collision, we see no change. Is that clear? Okay. So the only change that is occurring in momentum is in x direction. So now, and continue with all this, right? We can summarize what we have learned so far in one sentence. Due to collision, due to collision, the change in momentum of particles, due to collision, the change in momentum of particle is delta E equal to mv V cos theta, right, with a minus sign because this is final, that is minus mvx. I can also write minus mvx. Okay, final minus mvx minus initial mvx, right? But if I want to find magnitude, right, remember direction we'll figure it out, don't worry. So if we are only finding magnitude, you see I have not put arrow, it means I'm finding change in momentum's magnitude. Okay, I can write it like this also. So then that is going to be 2 mvx. Is this clear? Magnitude, right? This is only the magnitude. Direction we can easily find it out. There is no problem with that. Because it's going down, downwards is negative y, isn't it, Resha? And magnitude like direction nothing like simple. Okay, so this is the change in momentum in magnitude form. Now, what is the direction of this change? And that's what we are going to find out. What's the direction of this change? First of all, the momentum was towards right side. This is positive, that is towards the right side. Okay, right? But finally, the momentum turns towards left side. So the change is actually towards the left side. Right? I repeat what I have said. This ball was moving right side and downwards. After hitting, it moves left side and downwards. So downwards the same, no change with that. But the right side turned to left side. It means the change in momentum is towards left side. Okay, I repeat, the change in momentum is towards the left side. So this change in momentum is towards left side. Now another way to understand it, this thing is as follows. Okay, alternative. You can say that wall applies normal force on particle. Okay, in which direction? What do you think? When this particle will hit the wall will apply normal force on that particle. In which direction? Yes, obviously towards the left side. That's correct. Okay, hopefully you remember how normal force works, right? So, you know what does force do? A force always changes the momentum. Hopefully you remember that. So that's what has happened here, right? Because the wall applied normal force, towards left side, that's why change in momentum is towards the left side. Okay, so now this brings us towards the next sentence. So force on particle by wall is towards left. Okay, watch this carefully. Force on particle by wall is towards left. So this is action. Now if you think of its reaction, therefore force on wall by particle. I hope you understood what I mean. Force on wall by particle is towards the right side. Yes or no? This thing clear? Okay, this sentence is the origin of pressure. You see, what this means is when a molecule comes and hits the wall, when a molecule of gas or a particle of gas comes and hits the wall, this molecule is going to apply force on the wall in the right hand direction. So, you know, if I just want to indicate it as follows. This is going to be force on wall by the molecule. Okay, FW. Now you know that whenever such a force acts, right, you can always find pressure, right? Pressure is going to be force divided by area. Because there is a force, there is also a pressure, right? Okay. So how much pressure is there? That's what we are going to find out. Okay, so now we are entering the critical part of the calculus. Listen to this carefully. Just saying force is not enough, Gracie. You'll have to say force on what by what. Okay, normal force on particle is left side and normal force on wall is the right side. Okay, so now we are going to find out, listen to this carefully. This is what happens when one molecule hits. Okay, we have calculated all this for one molecule hitting the wall. Okay, now we are going to find out what happens when the billions of molecules in a gas hit with a wall, right? And they apply force and pressure and all that. Okay, so let's start with that part. So suppose in container, okay, in a cubical container, you understand what is cubical, right? Cube of side length L. What the side length? Let's say L, right? There are, let's say, n number of molecules of gas. Okay, and each has mass m. Whose mass is m? One molecule's mass is m. One molecule's mass is m. Okay, right? So if you would consider that there is a cubical container which is suppose oriented along the axis like this. Okay, and I'm sure you would have understood what I did here, right? So if we focus on this wall, okay, only on this one, right? The right side wall, જેવું આપણે પહેલા કર્યું એટલે એ બધું આમાં use કરી શકીએ. Suppose this is x axis, here is y axis, and here is z axis. Okay, right? So now can you imagine that here there are going to be so many tiny molecules moving here and there? Is that okay? Right? Okay, this picture clear up to this point? So I am going to make a statement that is a little weird, but it's still correct. Okay, it will take some time to get used to it. Listen to this carefully. It is that in some time interval, in some time interval, let's say delta t. Okay, in some time interval delta t, we can say that half of the molecules move towards the right wall and the other half move towards left wall. Okay, so we can say that half of the molecules move towards the right wall and half of them move towards the left wall. Now, why would this be true? Okay, this sentence is true only because of random behavior. Okay, do you remember I told you that molecules are moving here and there randomly? So basically what this means is that half of them are trying to move towards the right side, whereas other half are trying to move towards left side. Okay, not just because container is stationary, but also because of random behavior. Suppose they all would start moving towards one side, then that is not called random behavior. I hope you understand what is meaning of random. Okay, so right, also here we have not even considered vertical, means y-axis, and we have not even considered z-axis. Right now we are only focusing on the x-axis, that is moving left or right and hitting either wall number 1 on left side or wall number 2 on right side. Some move up also, agreed, but do you remember that the axes are independent? So whether a molecule moves up or down has no effect on whether it moves left or right. Here, I repeat what I have said. How the molecule moves in y and z has no relation with how it moves in x and y. On x-axis. So that's why this sentence is still true. Even if the molecules might go at an angle, molecule goes like this, then it is still true that it is moving towards wall 2. Understand? Molecule is moving at an angle. Then it is still true that the molecule is moving towards wall 2. Got it? अरे वॉल 2 ની નજીક તો આવે જ ને, જેમ ત્યાં એક વોલ છે ઉપરની સીલિંગ કો આમ જાય. Is it not coming closer to wall 2? Is it not moving towards wall 2? Think about it. Okay. Hopefully you got that idea, that even if it is going at an angle, you can still say that this one is moving closer to wall 2. Okay, so half of them are moving towards right wall and half of them are moving towards, it is moving upwards, I understand, but you forget this thing that xyz axis the motion is independent. Suppose a plane, let's say this is a runway and this is east and this is west, and let's say a plane is taking off from here, right, and let's say it goes like this, then would you only say that plane is moving towards sky? Would you not say that plane is also moving towards east? Right? So components are important, remember, and don't forget independence of axis. Like I said, moving up and down has no relation with moving left and right. Okay, even if something is moving up, it can still be moving towards the right side if it is moving at an angle. Okay, so like I said, half of them are moving towards the right side and half of them are moving towards left side. Okay, so if there are n molecules, right, if there are n molecules, then I can say that in a time interval delta t equal to L by Vx. Of course, you are right, Marvin. So in a time interval delta t equal to L by Vx, in a time interval delta t equal to L by Vx, n by 2 particles will hit or will collide the right wall. This is something very crucial. So what does this mean here? We are saying that if you would take a time interval which is equal to L by Vx. What is L? L is the side length. Don't forget. A cube ni side length is L. Okay. So now imagine this here. Let's say this is that cube. Okay, I'm just drawing a rough diagram. If a molecule starts from the left end and now is moving towards the right end, okay, and its x component of speed, or sorry, x component of velocity is Vx, then do you realize that to arrive at anywhere on this right wall, to hit somewhere on the right wall, it will take a time t which is equal to displacement in x axis divided by the speed on, the velocity on x axis. Did you understand this? Of course, you might have a question. Would it not collide with something? It would, right? We know it would collide. But what will happen is that if this one will collide, it will actually pass on the speed or velocity to something else. For example, what will happen is, suppose this is moving towards the right side, and let's say it's going to collide with another molecule that comes like this. So what will happen is that when the green one will hit the pink one, right, when the green molecule hits the pink one, it's going to throw pink one back there, and then instead of going towards the right side, the green one might go there. So khali farak શું પડ્યો? The molecule got exchanged. What I mean to say is, earlier it was the green one which was going to hit the wall on the right side, but now instead of green, the pink one is going to hit the wall. Did you understand? Okay, so it's going to be that half of the particles, half, because half of them are moving towards the right side and half are moving towards left side. Okay, I was waiting for that question. I'll explain that here. So half of them are moving towards right side and half of them are moving towards left side. So that's why ultimately this thing will not change, right? કારણ કે એક ગ્રીન ના બદલે હવે પિંક આમ જાય છે. ઓકે, હવે પિંક ને કઈ બીજો યેલો ભટકાશે તો એ પિંક આમ જતો રહેશે પાછો અને યેલો આમ જશે. So like that, what's going to happen is that the number of particles that are going to hit the right wall will not change. Now there is a question here, okay, from one of you. The question is, how do we know it's exactly half? You know that more particles are going towards right side and more or less particles are going towards left side. Okay, that kind of situation. Why is it not possible? Okay, how many of you had that question in mind? એવું કે તે ખબર પડી કે equal જ હશે, અડધા આમ ને અડધા આમ, right? Okay, right. So many of you have that question. Very good. I'm pleased that you have that question. It is one of the essential things about this chapter. Okay, I'll answer that question, but before that let me just answer a very small question asked by Jay. Will green transfer energy to pink? Yes. Okay, possible. It can do that, right? Yeah. Okay. No, Resha, that's a part of the answer, but still not the biggest reason. So what's the reason why I'm saying n by 2 here? Okay, why exactly half? To understand that, you need to understand randomness. Okay, how random things behave. Okay, think of a dice. Dice the ખબર ને શું હોય, right? Okay, so if you take a dice and let's say you roll it 2 times. ચલો આના કરતા easy example વાંધો નહીં, આ પૂરું કરીએ પછી બીજો example. Let's say you take a dice and you roll it 2 times, right? And we group things into 2 parts, 1 2 3 and 4 5 6. Suppose you get 1 2 3, you lose, and suppose you get 4, 5, 6, you win. Okay, let's say there's this kind of game. So do you agree that there's 50% chance of winning and 50% chance of losing? Yes or no? Very good. Now, suppose you roll it 2 times, only 2 times, right? Then it is possible that one time you'll get 1 and one time you'll get 2, okay, and you will lose both the time. Or it is also possible that one time you get 4 and one time you get 6 and you win both the time, right? You understood what I said? Yes, no. Very good, Dia. You understood where I am going. Okay. Now, while this is for 2 times, okay, and you have studied probability in 10th standard. So, what's the fact? Suppose instead of 2 times you make this these many times. Till a times 2 lakh times. Okay. Schools are not working. You have nowhere to go. You have plenty of time at home. Okay. Do this 2 lakh times. So when you do that, suppose instead of 2 lakh, let's say you do it 6 lakh times. So you are going to note that you get nearly 1 lakh times 1. Get nearly 1 lakh times 2. You understand what I am saying? Yes or no? Hopefully everyone is thinking of probability, because this is probability in nature. So we say that probability is a law of large numbers. Probability is a law of large numbers. What does that mean? It means that when you are observing something with large numbers, okay, then probability becomes amazingly accurate. Probability becomes amazingly accurate. What does that mean? If you roll the dice only 6 times, then there is no guarantee that you will get 1 one time, 2 one time, 3 one time. You understand what I am saying? This is nonsense. Understood? But if you do that, let's say 6 lakh times, which is a large number, obviously, I'm sure you'd agree that 6 lakh times is a large number. Okay? So then probability will start to show its magic. So you will get that nearly 1 lakh times you get 1, nearly 1 lakh times you get 2, and so on. So why am I bringing all this up? What does this have to do with gases? It is that a molecule, okay, in a gas, this n that is number of molecules, how many do you think there are? Suppose there are only 2 molecules. Do you think there are only 2 molecules in a container of gas? There are going to be billions of billions of billions, isn't it? Not just 6 lakhs also. Much bigger than 6 lakhs. Right? The number of molecules that you are going to have is going to be much greater than 6 lakhs. So what will happen? It's that when you consider random behavior of molecules, random એટલે આમે જઈ શકે આમ જઈ શકે આમ જઈ શકે બધી બાજુ જઈ શકે. So do you realize that there will be equal probability for a molecule to go left and to go right? Did you understand? Equal probability to go left and right. And equal નો મતલબ થશે 50%. 50% chance it will move leftwards, 50% chance it will move rightwards. Understood? So how many of you got this n by 2 now? Do I really know it will be exactly n by 2? No, joke. હું તમને બહુ ક્લિયરલી કહું છું. I don't know whether it will be exactly n by 2, but it will be more like this. Suppose let's say you've got 1 mole and you very well know what is 1 mole. So 6 into 10 raised to 23 are there, let's say. Then it's possible that instead of 6 into 10 raised to 3 is half, you might have 10 more molecules hitting the right side. તો એનાથી શું ફરક પડે? આ નંબરની સામે આ તો બહુ જ ઓછું છે. It's really very negligible. I hope you got what I'm saying, right? So I really don't know whether it will be exactly n by 2. Okay, so that's why it doesn't matter. It would be a little bit more, a little bit less, no problem. But because it's such a large number, okay, 1 mole would be such a huge number. So that's why we can very well rely on probability and not have to worry about this extra 10 that might be there. Okay, we simply don't care about that. Okay, probability is going to work for us, right? Hopefully, sure. Right, so there's 50% chance that it would move left, 50% chance it would move right. Similarly, 50% chance that it would go up, and 50% chance that it would go down. બધી બાજુ opposites માં 50% chance, half probability. ચલો હવે આગળ. So I'm saying that if we give it a time, how much time? L upon Vx, then the molecule that was on the extreme left, that will also come and hit the wall on the right side. So in time L upon Vx, half of the particles, that is n by 2, will hit the right side. So now, okay, now we are going to continue on the next page, right? So I can say in time interval delta t, number of collisions with right wall, number of collisions with right wall is n by 2. Right? Number of collisions with right wall is n by 2. Again, what is this delta t? Delta t is equal to L upon Vx. If we allow that much time, then there will be these many collisions, n by 2, with the right wall. Okay, there will be collisions with left wall also, but we are not concerned about that. એનું જે થવું એ થાય. પહેલા right wall નું observe કરીને study કરે, પછી left wall ની ચિંતા કરે. Okay, so you can say therefore momentum change due to these collisions is n by 2 into 2mvx. How can we argue? Do you remember earlier we thought that if a molecule hits, then the change in momentum due to one collision was 2mvx. Did you write it from the earlier part of the derivation? So it's like for one collision it is change in momentum 2mvx. Then for n by 2 collisions, how much? Okay, that's what we have done. Right? Okay, so this you can say as delta p total. Right? Okay, this you can say as magnitude of delta p total. Now, this is happening in some time interval. Don't forget. This is happening in some time interval. That's it. So I can say next step. Therefore, average force on right wall. That's it. Whenever one molecule hits, it applies a force. Okay. So average force on the right wall is F equal to delta P total divided by delta t. I hope you got that. This is only magnitude once again. Direction तो आपने खबर है. If you take the right wall, then the force on the right wall because of molecules is towards this side. I hope you remember that. Clear this step? I have used Newton's second law. F equal to delta P by delta T if you are finding average. Okay, let's go to the next. Let's put these values. So delta P total કોણ છે આ? નંદિની, ન્યૂટન સેકન્ડ લો બરાબર વાંચી લે. There are force is not equal to pressure upon area. ક્યાંથી લઈ આવી તું આ? Delta P total upon delta T. Okay, so let's put that here. N by 2 2mvx, right? N by 2 2mvx. Pressure હજી આગળ આવશે upon delta T. Delta T equal to L upon Px. I hope you got this simple step. ખાલી value you kind of. So let's cancel and put things. So 2 cancel, and this will become n into m into vx square upon L. Okay, so this is the average force acting on that wall. N into m into vx square. Now, if this is the average force, then we can find the pressure. Therefore, pressure acting on the right wall due to the gas. Remember, due to the molecules or due to the gas, right? Because gas molecules are heating. So this pressure is given by, hopefully you remember, F cos theta by area. याद है ना? But thankfully, yes, or you will also write F perpendicular by area. Okay, so here it's easy for us. This force itself is perpendicular. You can see that. You don't have to worry about finding components. See the F ni value લખી નાખો તો ચાલશે. Ultimately, this will become F upon A because F is same as F perpendicular here. Okay, so F upon A. How much is F? यहाँ पर लिखुં છે n m vx squared upon L. Now divided by area. Area whose area? Wall's area. So wall's area L squared, isn't it? Wall's area is L squared. Okay, now L into L squared, L cube. That is nothing but L cube. L cube શું હોય? L cube is volume, isn't it? Of this cube. L cube is volume. Capital V. Okay. હવે થોડું gas equations જેવું આવવા માંડ્યું ને. So we have P equal to capital N small m vx squared divided by capital V. Now let's go over to the next thing. You can say that n into small m should be equal to mass of gas. Do you agree with this? Ready to explain this? Clear? This is clear or not? N into m is mass of gas. Okay. This we are going to write as capital M. This we are going to write as capital M. N is number of molecules. Starting માં લખાયું હતું. Okay, so capital N into small m is mass of gas, right? So you can write the same equation as follows. Okay, I hope everyone got that. Now, what we are going to do is we will convert this equation to other forms. Right? We will convert this equation to other forms. We have got a basic relation. Density આવી ગયું ને ક્યાંથી આવ્યું શું આવી ગયું, right? We have got this relation. Now we will convert it to other forms, right, which uses temperature and all that, right? Okay, so let's have a look. First of all, I'm going to once again talk about independence of axis and random motion. When you consider both these things together, we have an important point to make. It is that on an average, our triangular brackets are average. Okay, triangular brackets mean average. Average of Vx squared will be same as average of Vy squared will be same as average of Vz squared. Now why should this happen? What is meaning of random motion? Molecules are going here and there everywhere, right? So just like we did, listen to this carefully. Just like we derived this so far for a wall, right? Derive this for a wall like here, this one, and here the molecule was moving towards positive x, so we said that right side, left side. Just like that, can you imagine you could do the same thing for this upper wall? Okay, and there you can consider molecule moving up and down. So James, આમાં Vx આવે એવી રીતે ઓલામાં Vy આવશે. Does that make sense? Okay, and what is meaning of random કોને કહેવાય? Random કોને કહેવાય? વિચારો. Random means truly here and there. Okay, no preferred direction. Right? If it was more in x, then we would not call it random. Random no meaning is like that there is no preferred direction. No preferred direction. Okay, so that's why whether you do this kind of calculation for x axis, y axis or z axis, on an average you are going to get same. Right? Now why is the need to take average? It's time to tell you that. Okay, so I hope this is clear that x, y, z doesn't make any difference. That part clear? Why do we need to take average is what I'm going to explain. Everyone, not a matter. Everyone is quite high. Yes, it is that because of random motion, if we say one molecule is moving, and let's say its x component of speed is v, then another molecule that might be moving, it's possible it's moving fast, so its x component will not be same. You understand what I said? For different molecules, Vx value will not be the same. Do you understand that? कोई मॉलिक्यूल फास्ट जाए, कोई स्लो जाए, अलग अलग एंगल्स पर जाए. That's why what happens, the Vx values are not same. આ formula use કરવી હોય suppose તમે. Okay, let's say we got till here. Now if you want to use this formula, then the problem will be which value of Vx will you put, because every molecule has a different value of Vx. Did you understand? Sure, clear? Every molecule has a different value of Vx. So if you want to use this formula for the entire gas, remember we did this for entire gas. See, I said that this is not just force because of one molecule. This is the average force when there are n by 2 collisions. This is the average force when there are n by 2 collisions. So there are so many molecules involved, and all those molecules, they don't have the same speed, right? So So that's why it is important that we take an average before we can use a relation. And that's the reason why I am talking about taking averages. Okay, so the next thing that I'm going to write is using this idea. Okay, that's where we are going to stop. So I can write P is equal to M average of Vx squared by V is also equal to M by V average of Vy squared, and is also equal to M by V average of Vz squared. Is this step okay? Again, why are the three equal in x, y, and z? Because the motion is random. And random નો meaning એવો થાય that there is no preferred direction. તો જેવું x માં જાય એવી રીતે y માં જાય. Also don't forget x, y, z are our choices. Right? Gas ના molecule ગમે ત્યાં જતા હોય. You could take x here. તો શું એના કારણે બદલાઈ જાય? No. So that's why there is no preferred direction, and x, y, z is all more or less the same, whether you consider this or that. And why did we take average here? Why aren't we just putting Vx directly? Because different molecules have different speeds, right? Okay, and that's why their Vx values are also going to be different. If you want to use this relation combined for all the molecules, you should definitely take some kind of average, otherwise it's not going to work properly. Okay, so this is the step where we stop today. All right, you make sure you go through all this. Right? હજી એકય formula derive થઈ નથી. Don't worry. It is a very long derivation. At the end, you get 2 or 3 different formulas immediately. Right? Okay. Make sure you go through the steps. કારણ કે step સમજાશે તો જ ખબર પડશે શું કઈ રીતે. Okay.